resistor is a device that limits the flow of electrical current in a circuit. Their uses in electronics are endless. Right now, we're going to have a look at how they behave when they're connected in parallel and in series. Welcome to Scofflaw Laboratories. We're going to connect some resistors, take a few measurements, and do a little math. Let's start with series resistors. And that's a schematic of two resistors in series. Their total resistance is R1 plus R2 plus as many resistors as you have in this series. So let's put a couple of resistors in there. The color bands give their values, but I'm going to measure them for more accuracy. And R1 is 62.2 K ohms, and K is 1,000, so that's 62,200 ohms. And R2, 262,500 ohms. We have our two values, R1 and R2, and the formula just says that we add them. So let's add them up. We took our two values and we got 324,700 ohms. Let's connect them on the end and take a measurement. We'll look at that. We calculated 324,700, and that's exactly what we measured. Now we're going to look at parallel resistors. These are two resistors in parallel. Notice they're connected on either end. Now the total resistance is the product of R1 and R2 divided by the sum of R1 and R2. Let's put those same two resistors back in. And we know their values, so we'll take their values and plug them into this equation. We have the product of R1 and R2 divided by the sum of R1 and R2. And when we simplify that fraction, we have 16,327,750,000 divided by 324,700. And when we simplify that, we get 50,284.87835, and that probably goes on forever. Let's connect them and take a measurement. Now I can put my probes anywhere on either side here and get an accurate measurement. And we have 50,200 ohms. We calculated 50,284.8783, etc. And we measured 50,200 ohms. That's well within 1%. Now let's look at what happens when we have three or more parallel resistors. Here's three resistors in parallel. Now the total resistance is 1 divided by 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3, and as many resistors as you have in parallel. So let's put three resistors in place here and take their measurements. R1 is 2,312 ohms. R2 comes in at, wait for it, 289.6 ohms. And R3 is a whopping 11.8 ohms. So we have our three values. We're going to plug them into this equation. We took our three values We put them into this equation, and we get this big compound fraction. So let's put this in the calculator. We have 1 divided by parentheses, parentheses, 1 divided by 2, 3, 1, 2, close parentheses, plus parentheses, 1 divided by 2, 8, 9.6, close, plus parentheses, 1 divided by 11.8, close, close, enter. And we solved this big compound fraction and got 11.28269236 ohms. Let's put the jumpers in and take a measurement. .3 ohms. We calculated 11.2826, etc., and measured 11.3. That's well within 1%. Let's do a quick review. In series, the total resistance was the sum of the two resistors. But in both parallel connections, the total resistance was lower than the lowest resistor. Let's think about why that might be. If we compare it to a highway, series is like one lane of a highway being open. There's going to be some resistance to the flow of traffic. In parallel, it's as if additional lanes have opened, so there's less resistance to the flow of traffic. And that's how resistors behave in series and parallel. The math wasn't hard at all, and math is always a little easier when it has some meaning. If you saw my video on series and parallel capacitors, then the equation should look very familiar. So grab a few resistors, take some measurements, and do a little math, because this is how you assimilate these ideas. And then come back to Scofflaw Laboratories for some more electronic basics.